Alrighty. How about now? Can anyone hear me? Alrighty. How about now? Should be getting some audio through. Should be good. Alrighty, that's a good start. How's the lag though? I feel like that might be a bit of an issue ultimately going. Because, of course, it's probably going to take me a while to get deal with all my whiteboard issues. So if you're there in chat, be great if you could just say hello so I know who's here. So I'd like to say hello to you peoples. Okay, that means the lag is really quite bad. It's not what we want, but so I guess I'm probably just gonna have to try and space things out a little bit to make sure that people have the chance to ask questions and Alden and Nick have the opportunity to tell me where I've done stuffed up, because I probably will do that a fair bit. Yeah. Yeah, I can see that. Um, so I suppose the question is would people prefer this live stream type session to something else? Because I'm happy to keep going on this now that I've got the audio working, but would we prefer to do something else is the question. Given that it's not really going to be very interactive. It's going to be more like a lecture, and I'm not fantastic at lecturing. Okay, well, I suppose we're going to start the stream now for Graph Theory 2. Well, I think I might as well start Graph Theory 2 now. So, hello everyone, my name's David. I'm an OCM here at PCS if you don't know me, and I am attempting to live stream Graph Theory. Last week we had some rather serious audio issues, so I couldn't actually get anything working, and And to remedy that problem, I had to end up switching from my preferred Linux operating system back to Windows to get OBS working in some degree of certainty with proper NVIDIA drivers for hardware encoding. But this isn't what you came for. I'm sure you have all come for graph theory too. So last week we covered off a basic introduction to graph theory, and we covered off some of the core kinds of graphs and had a brief look into some algorithms that are working. So if you haven't seen the introduction to graph theory or don't know what a graph is yet, don't worry, because we're going to throw through a little bit of revision first. You'll have to excuse me as I'll probably be popping back and forth between a bunch of windows, because I only have a single monitor set up at the moment, which is not ideal, and to get a second monitor set up is perhaps a little bit difficult at the moment. And of course, from what I can see, the stream is delayed by about 30 seconds, so if you have a question, please chuck it in the chat, but realize that it might take me a little minute to respond, because that's just how this is going to work for today until we can sort out some slightly better settings, and there's been talk of moving to Discord, which doesn't sound too bad to me. So we're going to start off with what a graph is. I'm going to go with the non-mathematician way of doing it, and it's just a set. The mathematician way is a set of vertices and edges. The non-mathematician way is it's a bunch of circles and lines, and you just draw lines between various nodes. So what I'm going to try and do here is I'm going to attempt to bring up a super technical solution to the how do I whiteboard on a desktop with no touch input. And this is going to be, how am I going to get this string thing working? Alright. Okay, so that should be able to go there just fine. And this, I'm just going to spend a little second resizing my window so things will actually be able to fit in properly. Nice. And no, I'm just checking. So what I'm attempting to do right now is connect my projecting to this one. Yep, this up, yep, cool. Rightio. So, what I'm attempting to do is, you'll notice here, is I am attempting to project my display such that you guys can see it. And if everything's come up, hopefully OBS has registered this. That's not good, because you see, a small problem for me is I don't have touch input, which makes drawing on a whiteboard very difficult. And I tried to draw on a whiteboard last time, an actual physical whiteboard. Oh, and it's just disconnected me. Thank you very much. That's just what I wanted. Alright, this may take us another second. So yeah, you guys ought to enjoy. We might have a few issues with the whiteboard going forward. Hopefully we can get something up that's of reasonable quality. Alright, let's try again. Alright, connect to Mondo. Cool, connect to Mondo. I think we'll just end up doing it this way, that I'll just go full screen whiteboard. No, we're not going to go full screen. Alright. Alright, so can you guys see my whiteboard correctly? That's probably an important question. Now we go to OBS, go okay, that's good. Alright, so you should be seeing some slightly weird things happening in the stream. Okay, so we have pen input, which is nice. I enjoy pen input. Except it's not OneNote. Do I have OneNote on this thing? That'd be nice. That's fine. Alright, so we'll start off by doing a graph. You have to excuse that the editing process on this is going to be quite difficult. So, graph. Order of, we have G, we have a set of vertices, and we have a set of edges. They're pretty cool. Alright, let's see. Bring this back up, bring that back up. Sweet. So we have a whiteboard. That's good. I'm glad to see that. So essentially what the whiteboard is, it's an old Surface laptop from about 5 years ago that has touchscreen capabilities that I'm cannibalizing to use this. So we have a graph. Graphs are cool. We have vertices and edges. So vertices, there can be as many vertices as we want. We can label them however we want, and we have edges. Graphs can be both directed, as you can see below, or they can have edge weights. Or weighted, we call it weighted. They can be both directed and weighted, which is what most of your classic applications will have, or not, but that's the main key. There's one particular kind of graph that we are going to want to pay attention. Oh, why are you coming up, keyboard? Thank you, keyboard. I don't need you. There's one particular type of graph that you probably want to be aware of, and that is a DAG. Otherwise known as a directed acyclic graph, and that's simply a graph that has no cycles in it and is directed. DAGs can be weighted. So, as you can see our example from above, as soon as I draw this here and here, this becomes a cyclic graph, and we don't like that. We do not like that at all. Alright. So, next thing we want to revise, we want to make sure we remember, is we want to remember that what paths are. So path is just a sequence of vertices or a path through a graph. So if I draw an example graph below, that looks kind of weird, but maybe not so weird. You have to excuse my artistic skills. I am by no means a visual artist. In fact, I can't draw at all. In this particular case, an example path through the graph is we could go from 1 to 2 to 3. That's an example path. We could go from 1 to 4. That is a valid path. We could go from 1 to 2 to 5. That is also a valid path. Or we could start somewhere else. We could go to 2 to 5, back to 2 and back to 1. Because this is not a directed graph, which is also valid. So, and if we were to put some weights onto these edges, the sum of the various paths we would have, well, 2 to 5, that has an edge weight of 3. 5 to 2 also has an edge weight of 3. 2 to 1 has an edge weight of 1. So our total weight for that path would be 4. If you can see that in the corner. Which is not too bad. Just having a quick look at just want to have a quick look at how this is working. Okay, things aren't overlapping too bad, which is good. Always want to make sure of that. That you up there. Okay, cool. So the most important thing that we're going to be asked to do in relation to paths is we're going to be asked to find the shortest path, or what's the most efficient path through a graph. And the most efficient path through the graph, or the shortest path, is we can either define it in an unweighted graph to be the least number of edges you have to traverse. So if I were to draw an example graph this way, so here's my weird example graph that I just decided to draw. If I wanted to get from this node here, we'll call it A, to this node over here, we'll call it, how can I make this a shorter path? We can make that. We do that. And I want to do the shortest path to this node here, C. Well, that would just be the least number of edges. So I would go here, first to B, then I would go here and here. That's 1, 2, 3 edges that I have to traverse to get there. This also demonstrates that shortest paths are not necessarily unique, because I could have also gone, no, actually, no, that is the shortest path. That is unique shortest path, because this way it would be this would be 1, 2, 3, 4 edges. So I'll change my color here. This path through here would have gone through 4 edges. This path here would have also gone through 4 edges. And if I add another edge in here, this path going through this way would have been 5 edges. So the shortest one, which we actually will do, which I will outline in purple, because purple's royal color is great, would have been through these vertices. Now that in particular only really applies in the case of undirected graphs, whereas most of the time when we're asked to deal with shortest paths, we're dealing in a directed sense, or no, not a directed sense, a weighted sense. And so when we're not, you can't see what I'm drawing. Ah, bugger. Thanks for letting me know, Zara, that you can't see what I'm drawing. Um, hmm. Okay, so if that's not going to work, I'm going to try an alternative solution. This might be a little bit weird, but we'll see if we can pull it off. So, is it possible to attach this? Okay. That's not going to work, is it? let's see if this plan works. Let's see if this plan works. So right now I am attempting to position my webcam. Alright, let's see. No. Oh no. Okay, so this is a okay, so now that you can see the paper, I'm going to just go try cover that thing all again. So we were revising paths, and I apologize for the audio quality now, but so what's happening at the moment is my webcam is positioned on a water bottle that's directed at a piece of paper in front of the computer, which is perhaps not an ideal solution, and I think maybe with a second monitor that I can plug in a touch input device or something to might be of an assistance, but until then we'll have to deal with this. So if I was to draw a interesting graph, one that looked very weird like this, and I wanted to get from this node here, let's say call it A, to this node here, call it B. Intermediate nodes doesn't matter. In the undirected sense, which is what we have in front of us now, the shortest path would be the least number of edges we'd have to traverse. So obviously in this particular case we'd have to go from A through these two intermediate nodes. So I'm just going to label the nodes we go through with star. So we're covering these edges in our shortest path. Okay, thanks for letting me know that the audio's all okay. Apparently Sony headphones are good. Me being the latex guy, I imagine you expected me to have most of these diagrams done up in latex and TIX, and the short answer to that question is yes, I was intending to do that. The long answer is TIX has been mean, and I haven't had time to get everything done, because surprisingly it takes a good 15 to 20 minutes just to get a single diagram done. So, well, I hope you don't mind with paper for today. They'll be improved back in the future. So back to what we were doing, we have our shortest paths here. If we were to go through another path, say come along down here, that would take us through 1, 2, 3, 4 edges, or 3 nodes, which is a longer path. Things start to get a little bit more interesting, however, when we start directing the edges. So when we direct the edges, and let's say take this one, go back here, that can go there, that goes here. When we direct the edges, things become a little bit interesting. We can no longer just go down arbitrarily the closest path to us. So we can no longer go, in fact, I'll just remove this node outright. So in this particular case, our shortest path would actually be 1, 2, 3 nodes this way. So coming this node, and this node, and this node. So that's 1, 2, 3, 4 edges that way will now become our shortest path. And then to add the next little bit of complexity on, I will just redraw the graph because I don't have fancy colors now like I had with paint. Because despite what Windows said about, despite my opinions on Windows, Paint is a perfectly functional program that does mostly what it's intended to do, which is, I find, to be nice. So if we redraw this graph now, we start putting some edge weights on things. So if we say this place has 1, this is 2, this has another 1, let's say this one has 5, and if we put 2 and 3 down here, but we put 1 and 1, down here, actually no, and if I change this node to be going this way to make it interesting, let's go 1 here and 2 here, we have something to evaluate. So if we choose to take what would be 2 equal paths, so the first path will be go from, and I'll just label this B, C, D, E, F, G. So if we go A, B, C, D, E, so this path here, our cumulative sum of edge weights would be 1 plus 2 plus 3 plus 1. That would give us an overall sum of 7. Whereas if we were to take this path over here, we get 1 plus 2 plus 1 plus 1, giving us an overall sum of 5, which is much less. This is a shorter path. Okay, thank you for the feedback. Let's see if... Okay, if that's the case, let's attempt a different solution. So this should be slightly smoother. And if we go Logitech capture, come on, buddy. Yeah, that's fine. Yeah, devices ready for use. No. Video now is a bit bigger. Okay, so this can be a solution for now. You're going to get some really interesting artifacts and stuff, but this is just ensuring that I can see what's going on, which I think is going to be quite interesting. And you probably can't see it very well, so let's improve our lighting a little bit. Alright, that's some slightly improved lighting. Very weird. Wish it was better, but I think this is the best I'm going to be able to do for the time being. I can feel my computer struggling immensely at having to do a whole bunch of this stuff despite it being significantly beefy. This is why we were covering shortest paths. Shortest paths are cool, they're our friend. But covering a bit further on from last time, there's some different things that we can do to shortest paths. Are you gonna cooperate? No, that's fine. There are some different things that we can do to deal with shortest paths, in that we can look at things as from a single source. So allow me to get another sheet of paper, which I'm slowly running out of. And for those of you who are interested, I am recycling my paper. This was a reinforcement learning paper that I was doing another paper off of, and I printed it out a few times, so it's all fine for me to be using this as a scrap paper. So you can have a single source path. So if I was to apply it to the example that we have up on the board presently, I think for next year I need to once again put a bit more time into these slides, or do markdown slides. But if I were to apply it to this example, we could consider the case of a single source shortest path. So I want the shortest path from here to the shortest path to this node. And let me adjust the camera for you there. So this could be considered the single shortest path. as it turns out, when we look at a lot of the single source shortest path algorithms, we can essentially work out the shortest path from it to any other vertex for free, or perhaps not free is not the best sense of the word, but it's in the fact to guarantee that we get the optimal shortest path, we do have to evaluate every shortest path because we don't know whether whether there will be a shorter one at that case, in that particular case. So for getting the shortest path from A to G, we will inadvertently get the shortest path from here to here, which kind of hints at a little bit of a property that a larger shortest path will be composed of smaller shortest paths, but we'll get to that in a little bit as well. You also have the case of the single destination shortest path. And so what I mean by that is it's a little bit more subtle in that you'd think it's just, oh, okay, I'm just doing the reverse of the single source shortest path. Whereas it would just be the graphical inverse. And that's kind of correct, and I'm sure Nick will be all too happy to correct me here, but you do have to think a little bit harder about a single destination shortest path in that it depends on where your source is coming from, how you get. So if we want to get from this node to here, it depends on how far out you're willing to go back into the source. And the last kind of shortest path that we're going to cover here is the all pairs shortest path. And that's simply just what's the shortest path from every node to every single other node. Now, this can be calculated by using our standard source shortest path algorithms and applying them just to every possible start node. But as we'll see a little bit later today, there is a larger algorithm which is significantly more efficient at doing this, and we'll cover that. But all that would mean is, so what's my shortest path? And I'll just label these again. F, what's our shortest path from A to B, what's our shortest path from A to D, shortest path A to F, while also saying what's the shortest path from B to A, B to D, B to F, so on and so forth. So we're just calculating the shortest path for every possible occurrence of, well, every possible pair of vertices, which is an interesting combinatorial problem, is that how big is that set of vertices, but we'll cover combinatorics a little bit later. So we alluded to this just a little bit while earlier when we were looking at the single source shortest path, and that what makes a large shortest path work. And it's this optimal substructure that what we're talking about, is that essentially all the formal proofs of all the algorithms, especially for Dijkstra's and Bellman-Ford and the ones we'll cover today, all hinge on the fact that a large shortest path is built up of other shortest paths. And logically, that kind of makes sense if you think about it, in that if we have a large path, say a path of 4 vertices, and we say this is the shortest path from our start point to our finish point. If we remove our finish point here, and this here, and now consider this path here, we're looking at this path of 3 nodes, if this wasn't a shortest path, and in fact the shortest path to this node here was actually through an alternate node, we'll call that A, if this was in fact a shorter path to our new finish node, well then why did we ever consider this, I'm going to call this the stupid node, or the node we don't want to see. So I'm just calling it, what do I call it? I'll call it C, because we can call things whatever. And once again, we are probably not getting the resolution we want, so I'll try to outline things. Because logically, as if there was a shorter path to F through some intermediate node, well, why wouldn't we just take this longer path through to our other one and make it a shortest path? And that's what we mean by optimal substructure, in that every shortest path or sequence of vertices is built up itself of shortest paths. So going back to our original shortest path, the long one, this set of 3 nodes, that is the shortest path, and this set of 2 nodes is also a shortest path. All of the algorithms we're going to cover today hinge on that fact, that you have optimal substructure. And for those of you who perhaps have a keen mind, this might start sounding like a little bit of a dynamics programming problem, as we have oh wait, we have a thing, and then we can extend out our reach by one node. We're forming a direct acyclic graph with possibilities. We remember what we've done before, sounding a bit like a DP, and we might in fact get to an example of a DP later today. So we covered it very briefly last week, and that was Dijkstra's algorithm. It's our favorite shortest paths algorithm. If we remember, go back to once again, that was an order of v plus e. Very nice, time efficient, did what we wanted to do. And all it was is we were simply have a list of vertices that we have looked at and that are we can see, and we simply record in each vertex that is at the edge of our range what its cumulative path will be. So I'll just draw an example down here. I did have a visualizer up on the internet, but now that I have pieces of paper, I see no need to go back to the internet because pieces of paper is just far superior. So if I have my example graph here, and I'll just do some different things here. I'll label them. I'll adjust. And just for my own curiosity's sake, I'm going to have a quick look at our system statistics because I want to know. And as you can see, GPU is doing some work, which is, I think that's pretty funny. Our CPU is doing next to nothing. Cheers. That's all good. So, back to Dijkstra's. We are going to have a quick look at revision at how Dijkstra's work. And so I will weight these graphs. 1, 2, 4, 3, 5, 1. And what Dijkstra's does is essentially it has, for each node that it's seen, it records what the shortest path to that node is overall. So if we'll start at A, we'll go to B. So we've seen B, the shortest path to get to B is 1. It's the only node, so we extend our reach to B. Let's look at the adjacent nodes we have to here. So we have C, D, and F. So if we have C, D, and F, and in them, we simply store the cumulative sum of the paths we got. So to go from A to C through B, that will be a weight of 3. To go from A to D through B, that will give us a weight of 6. And to go from A to E, we also have E and F. E, that'll give us a weight of 4, and go to E, that gives a weight of 5. And these nodes here, which are stored here, are stored in a priority queue, such that each of these will be ordered in the order. So in this particular case, that would go there, and 6 would come to the bottom. But I didn't draw these in order, so this will be ordered such that when we take the node off the top of the queue, it's the shortest node. So next, we'd go have a look at C. And then we'd look at the same node closest to C. Well, that would give us D, so we'd look at D, and then after that, this node here would come off. And so basically at each stage, we're just storing what our current estimation of that path is. And as you can see here, we are kind of building up that optimal substructure, which is that A to B was the shortest path, B to C, A to C, well, this was the shortest path, A to D was also another shortest path, and that will generalize to the whole algorithm until you've looked at every single node. So we have a single source, shortest path to each and every node. For those of you who might be a little bit confused, what does the output of this algorithm, how do we actually get the physical path out of this algorithm? I have some code here, and what it actually ends up doing is it ends up building a shortest path tree. Almost all the shortest path algorithms build a shortest path tree, and so it'll say, what's the shortest path from A, and then it will go, well, the shortest path is to B, and then from B, it will go to C, and then D, and then everything else, and then you simply just have to traverse this tree till you get to the node that you're looking for, which is everything else. So if we look back at the slides now, we have a Python implementation. Thank you very much, Seamus, for sending this through. It's perhaps not the most readable, as he actually commented that, but we'll just go quickly through them. So we have our priority queue, which in this case will be a list, or in fact, the priority queue will just be, what we do is we turn it into a binary heap. So the actual implementation of what a priority queue is actually a binary heap, which is a pretty advanced data structure. I think we will cover it a bit later in the sessions, I think. I'm not entirely sure. And it should be all good. So what we do is we get our priority queue, we initialize this thing, let's just initialize all the vertices we have to be some rent, some 0 weight. We give our source vertex a weight of 0, and then we chuck on our source vertex. And then all of this here is just doing that thing. It says we look at our existing path that we have. If we have a path that's shorter, go through that path. Is all this saying. Is if we can find a shorter path from nodes we're looking at currently, go through that path. The next thing we're going to cover today is we're going to cover a topological sort. So a topological sort is an ordering of vertices, and it's what we're doing is we're ordering it in, I like to think of it as ordering it in discovery time from a depth first search. So if you want to keep your eye on the thing, I'm actually going to make the whiteboard a little bigger. There we go. Might help things out. So what we're thinking about when we're thinking about a topological sort is we're ordering the vertices in order of discovery time. So if I draw, I'll do perhaps a trivial example. So the first trivial example we're going to look at is we're going to look at a tree. If we were a valid topological sort ordering, and I'll just label these 1, 2, 3, 4, 5, 6, 7. So if you've noticed, I've labeled them in a BFS order, and we're going to let's just do a DFS on this tree, do a bit more revision from last week. So if I were to depth first search, we can either choose to go right or left. I'm going to choose to go left. We would go to 2, then 4 and 5 would be pushed on our stat. We go to 4, then we go to 5, then we come back up, go down to 3, go to 6, and go to 7. And so that would give us an order of 1, 2, 4, 5, 3, 6, 7. Which is an order of things. If you were to look at things, so this is a valid topological sort. Well, actually, this is one possible valid topological sort ordering. And if you look up there's a formal definition up on the slides at the moment, which I think is not particularly instructive, is that if there's a vertex, if there's an edge, so I'm going to come back to it, if there's an edge from one vertex to another, so from I to j, then vj comes before vi in the topological ordering. So in this particular case, we would have to reverse this whole list to get a valid topological sort ordering, but that's just putting everything down. Another valid topological sort ordering is the discovery time of a vertex in, well, actually, this is it's the discovery time. It depends on your interpretation of discovery, whether you mean it's when it's pushed onto the heap, is it when it's discovered? So that means 2 and 3 would be done at the same time, or when it's actually visited. I'm taking it as when we actually visit, go down and explore its children as the discovery time. Not the finish time, which is when we've explored all possible children of that node. So that is a valid topological sort ordering. Now, if we want some code for this, once again, LaTeX let me down in that doing Beamer and code listings doesn't really, they don't play nicely together. You have to do fragile frames. So we're going to get up our topological sort. Was this? So this is our topological sort implementation that I've done up rather hastily. Done in Python, of course, because we like Python, and I was too lazy to get the full C++ implementations up and running. All we're doing is we get our visited, our degree, we set initially our ordering, then we loop through all of our nodes, and all this is basically just saying is this is setting up all of our initial nodes in our matrix, because I've chosen to do it with the adjacency matrix representation, not the adjacency list. If we were to do this in adjacency list, you could effectively remove all of this. You could remove all of that if this was not an adjacency matrix. And so all we're doing is we'll say, have we visited this node? Yes, we visited it, so on and so forth. But this is just a whole setup. What we're mainly aiming for is we're mainly aiming for this part here. This is effectively the DFS of what we're doing. Now you will see that I've chosen to do this in an iterative manner because I prefer doing things iteratively because it is technically more efficient to maintain your own stack as opposed to letting the compiler manage your call stack for you by using the recursive method. But as you'll see later, it's significantly, it doesn't help as much. It's not as intuitive as to why this works, particularly in discovery time when this isn't done recursively and it's done iteratively like this. So all we're doing is we get the front of our queue, we append this vertex, so we've discovered the vertex, we append it to our topological sorting, then we look at the adjacent vertices, ones that we haven't seen before. We minus the degree, so that's just our time. So the reason why we have this degree here thing, this degree is essentially it's representing time. Now if I were to do this in a recursive manner, time is covered automatically because I'll just quickly go back to the whiteboard here. I'll quickly go back to the whiteboard down here. Is that if I cover something recursively, what will happen if I just draw up my tree? What will happen is I will start at this top vertex. I will call my recursive procedure. I look at this first vertex. The recursive procedure is immediately called on this first vertex here. And then we will look at the first adjacent thing here. The recursive procedure is immediately called on this vertex here. So discovery time is handled automatically recursively. And then once this one's finished, we go back up once again. Doing it iteratively and looking at things here, doing it iteratively, you kind of have to force your way out of doing a BFS. And what I mean by that is when we started our top node here, doing it iteratively, we look at all the adjacent nodes first. We actually technically do a BFS. We do this one here, and it's only the fact that we're using a stack that means we go down this one here. But if we were to record this as being the discovery time or the time, our topological sort ordering time, this node here would come before this node here, which is incorrect as opposed to our recursive definition. So what this implementation up here is doing is by setting this degree here, it's simply saying recording the time such that we don't stuff things up as opposed to our recursive definition. I'm not sure if that makes entire sense. Once again, trying to do things efficiently through a stack yet using Python, which is a fundamentally inefficient language, probably seems like a bad idea. Now I'm thinking through, kind of is, but some code for a topological sort. It's nice. And the main reason we're covering what a topological sort, it's, by the way, Albert will kill me if I don't mention this, and if you don't know who Albert is, you'll find out soon enough. Topological sorts are not unique. So if we go back to our original example over here, I could have just as easily chosen to go on right instead of left at my first, and I would have gotten a completely valid ordering. And I can choose to go in random directions as long as I don't go down the same node twice, and it maintains that property that V comes before J in the topological sort ordering. Yeah. It should be mentioned that the way I drew this down here in order of discovery time perhaps isn't entirely the way that would be done in code. We actually would use a stack to put things on in discovery time. So in the end, what I'd do is I'd push 1 to the top of the stack. Then when I discovered 2, I'd push 2 to the top of the stack. Then I'd push 3, then I'd push 4, then 5, then 3, then 6, then 7. So you do actually get the valid ordering instead of just writing it down in discovery time order. You push it onto a stack in discovery time order. Hopefully that makes sense. If it doesn't, not to worry, we will get through it. Next, we're just going to take a little bit, dive into a bit more theory-based things, and we're going to look at connectivity and connected components, because this is what we're leading here is we're leading into strongly connected components, and there's some very, very nice, I think, real-world applications for strongly connected components. So if we move somewhere else in our whiteboard, what do I mean by a connected graph? So if I draw this graph here, I would like to think that every node in this graph here can reach every other node through just one edge. Seem pretty simple? If I drew this graph here, it's still undirected. Every node can still get through every other node, but through a path, not just a single vertex. So what can we say about how these graphs are connected, or how the nodes are connected? In this example here, we can say that this is a completely connected graph, in that every node connects to every other node. And these are very, very nice graphs to work on, and really it's where adjacency matrix representations shine through, because your space requirements, you're not wasting any space as opposed to an adjacency list, and you're getting that free lookup time, which is very nice. Whereas in this one is just a connected graph. It's just standard. It's not any particular kind of connected. It's not particularly connected. If I were to draw something a little bit different, so if I was to draw this node here, and then draw these three nodes over here, so we're looking at this example. This particular group here, the graph is not connected, and there isn't a path that exists between every single node. So we have two individual connected components, in that even though this is just a singular trivial component, it's still connected because there's a path. We assume implicitly that there's a path from every vertex to itself. So, and these are all perfectly connected. So we've broken it down into connected components. This might seem all a little bit, boring and not very interesting. So we're dealing with undirected graphs, and in undirected graphs we can go wherever the hell we want, whenever we want to. The interesting notion of, and I incorrectly drew a diagram here. So the notion of strong connectivity only really applies to directed graphs. And what we're going to show is we're basically working up to strongly connected components. So this notion of strong connectivity only really applies to strongly connected graphs. And so what I mean by that is that if we draw a graph that looks like this, and say it goes like this, goes here, goes there, goes there, and goes there. So if we draw a graph like this, a graph here is strongly connected if any vertex can get to any other vertex through a path. So what was just standard connectivity up here in our normal notion in undirected has now become strong connectivity because we are now directed. We are now forced to take a path. So an example, if we go back to our trivial 4-node graph, this would be a strongly connected graph, in that every vertex can get to every other through a single node, through a singular path. In this particular graph up here, this particular graph is not strongly connected because this node here cannot get back into this half of the graph at all. So what this brings up of is kind of the idea of a strongly connected component, in that I can break this graph down into here because all of these nodes can reach each other, this because it can reach itself, and then also over here each of these also has to be its own strongly connected component. If I were to change the direction of this arrow to say here and here, then we would get a second strongly connected component. So all of these vertices can reach each other, and all of these vertices can reach each other. And this is very nice, because what strongly connected components are, they kind of, in my mind, they mirror road maps. And what I mean by that, or large, if you take a larger, so once again, excuse my crappy drawing skills, but we're going to draw a really coarse representation of Australia. Yeah, big Australian bite doesn't exist. I don't know, it looks something like that. Looks starting to look more like a cat. I don't know, I'm going to give up now. But let's say in Perth here, and we were to zoom in into what the Perth road, we could make a graph of roads that go between a whole bunch of different roads that look like this. And then we come across over here to Melbourne, and we have a whole bunch of different roads here in Melbourne. But there's only one highway. Well, there isn't in actuality, but pretend there's only one highway between Perth and Melbourne. Well, the strongly connected components are just the individual cities' roads, and the overall graph is the overall road map of Australia, or any country, or anything really. And so the way I like to look at it is it's just a way, if we go back up to this end, of abstracting out a more global structure in your graph. And depending on your graph, most of the time what you're going to find out is that your strongly connected components actually form a DAG, which is very nice and brings up all kinds of little tricks and tidbits that we can cover on later. So the algorithm that we're going to cover today for dealing with strongly connected components is called Kossaraju's algorithm. And Kossaraju's algorithm is I'm just going to check people are still here. So Kossaraju's algorithm is perhaps the most efficient strongly connected component has. There's also Tarzan strongly connected components and everything else, and there's a few other algorithms that exist around for it, but essentially what Kossaraju's algorithm does, and because we're going to cover it rather quickly, is we do our depth first search recording the finish time. So essentially what we're doing is we're doing a topological sort. You could think of it as that way. We reverse all the edges in the graph, and then we do a DFS again in the topological sort order that we got from the graph the first time. And as we look at all the components that creates, and you get your strongly connected components. Now, right off the bat, that's probably not going to make sense, and so this is why, once again, we're coming across to the trusty whiteboard, and we're going to cover a little example of how this would work. And I'll also bring up an implementation for those of you who would like to look up. So here is some pseudocode that I wrote up, half Python, half C. I'm not sure what I was doing. I think I decided I wanted to change it to Python halfway through. And not particularly important, just kind of embarrassing because I don't know what I'm doing, and this is fine. So let's go back to that nice, perhaps obvious version of strongly connected components. Now, once again, move the paper. You'll also notice here that strongly connected components kind of don't really care too much about weighting per se. But there's some interesting things we can do that. So what are we going to do first? Well, we need to do a depth first search. So let's arbitrarily choose a start node. Let's choose this node here. And I'm going to label these A, B, C, D, E, F, G, H, I. You probably can't see that on the webcam because this is not a fantastic webcam. But I think we'll do it. In fact, I'm probably just going to wait a bit. Do we want to take a quick break now? Just a general question to chat. apologise for this awkward 30 odd seconds of silence. So I really need to get a drink. Did not come prepared. Alrighty, we're back once again. 30 seconds of delay before you're actually able to hear what I'm saying. It's fine. I'm just admiring the fact that my air conditioner is only really just able to overall equalize my PC from doing all this stuff. So, back to Kosaraju's strongly connected components. So what we're going to do is we're going to do a DFS. So from A, we're going to get to B. So we'll make a little stack up here. So we start with A. Next up we go to B. Then we end up at C. Then we will end up at D. And then basically, once again, we'll end up at E, F, G, and then H, I, J, K, because I kind of wrote them out in the order that you do a DFS on. So we have an order here. So we have the I, H, G, F, E, D, C, B, A, which is nice. Now let's reverse all the edges in our graph. Probably going to make a mistake here. That's good. Let's go here. Over here. No, that one goes this way. This way. Right. Cool. So now we have our nodes again. And then what we do is we do a second DFS order. So what we do is we pop our first node off the stack. Let's go I. Let's do a DFS from, actually no, here, that one, that's fine. That's fine. Yeah. So let's do a classic DFS from I. We'd get I, we'd get, anything else? No, is that just going to do what I want it to do. Yeah, so we start with here, we go I, we get our first node here, then we get I, and then we get H, then we get G, doing what I want it to do. No. Yeah, then we get G, and then we would get F, so we get our first strongly connected component. So we get that. We've already seen all these members. Then we pop off E. E will get us to here, 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 here. And that will give us the strongly connected component for E. And then you get the second strongly connected component off the end. I think I made a mistake here because you keep going back through the whole graph again. I've forgotten what did I do wrong? So yeah, we just put this adjacent to this, then visit the nodes, DFS order, and do another DFS. Should I forget to do the reverse order thing again? So start from I. Yeah, I think I did. I did something in reverse order, which is rather unfortunate because I implemented this algorithm yesterday. It's not fun. But essentially, for the sake of time, you essentially end up getting back your strongly connected components. And if you want to see a better implementation, I'll be including in that the slides that I put up on the website, which is interesting. We're going to take a trip back into Pathland now, and we're going to look at something called the Bellman-Ford algorithm. Yeah. I think we'll fix up my example for the meantime. I mean, if I am particularly desperate, we can head on over. I have this fancy online demonstration of topological sort, and so we'll do a topological sort, and then as you can just see, we just do our DFS. And then we would go through, do our DFS, and we get our topo order, as you can see. So you get your topological sort order. This is a very nice program. And then we get our final one. Cool. And so yeah, you've got topological sort. So just you do your topo sort, and then you reverse the edges, and then do another topological sort. Yeah, I think I've kind of stuffed that up a bit. Whoopsies. It's fine. I don't even. We'll be right. So yeah, next up we're covering Bellman-Ford. So this solves essentially exactly the same thing that Dijkstra's does. It deals with negative edge weights, but it's slightly less worse complexity. What I mean by, if we remember where Dijkstra's kind of failed, Dijkstra's fails on negative weight edges. And to show you a very simple example of what I mean by that, is it just means you can be drawn down a path that's really not good for you. So if I was to take, say, this very trivial example, and I have a 1, I have a 2, and I have a negative 1 here, and then here, let's just put something stupid like 50. Dijkstra's would see going to here as an overall weight of 0, but it would see here going as an overall weight of here when at the time it's at vertex 1. So it would be tempted down the path of negative 1, it would see the 50, and it would no longer have the choice back go band 2, so it would think the shortest path is 49, not 2.
We're walking and you're cooking later.
I'm streaming.
Okay. You're still cooking.
So yeah, for all those in there, I'm definitely promoting it. Quarantine means fun things, and I am on dinner duties tonight. I'll be doing some homemade lemon chicken. It'll be pretty nice. Hope you're all doing well and staying safe these Corona holidays, except they're not really holidays because we're all still working. It's not ideal, but nevertheless, Bellman-Ford. So Bellman-Ford deals with these negative edge weights where Dijkstra's fails, because Dijkstra's was just greedy. It'll be tempted down that path. If you introduce negative edge weight cycles, you will just go in them forever. And the definition of a sort of shortest path it's not well formed, it doesn't make sense. So, how's Bellman-Ford work? You relax all the edges for all your vertices. It seems pretty simple, but essentially we'll cover what relaxation is. So relaxation is just you maintain an upper bound on any particular node or a path to any particular node, and then as you see more vertices, or as you go further and further through the graph, you progressively update that estimate that you have. So if I was, it seems very, very similar to Dijkstra's, but what it does instead is it doesn't greedily select which ones it goes down through. It just continues. It does a relaxation policy. And so I'll just give a quick example. So if I have this particularly simple graph here, and we'll maintain a rate, so A, B, C, D, and I'll just make this a little bit interesting. Let's go E, F. We've got, and if we put some weights on here, let's say 1, 2, 4, 3, 2, 1. We're going to have, that's actually kind of dumb. Okay, let's put that as 1 as well. Okay, so what we're going to have is we'll maintain an estimate. So the shortest path from A to itself will be of weight 0. The rest will just be infinity. And then what we do is we just explore a vertex. Let's just explore a vertex. Let's go to B. Well, the shortest path to B is 1. That's all we know. And we don't know anything else at this stage. So, we know that the shortest path to B is 1. We know that the shortest path through C, well, that's going to be 1 plus this 2 here. That's going to be a 3. And we don't know anything else at this stage. We know it's going to be a maximum, an upper bound of, we still don't know what any of these are. So, let's go have a look at C, explore what C has to offer. So it tells us that it's an upper bound for the path through C is going to be 1, 2, 3, 4, 5, 6, 7. And over here we get 1, 3, 7 as well. And then this last part here, if we go down E first, we'd get an upper bound for this to be 5. Well, actually, no, sorry. So 7. We get 8 to be the upper bound for here. Actually, that's 6. But if we go through here, well, we get a path of 7. So we get an overall path, and we'd relax that edge finally down to 7. So all the fun bits of what relaxing does kind of happens down here, but it's essentially you're going through the graph, exploring a whole bunch of things, and slowly getting a more accurate and clear picture of what the actual paths to these vertices are. So once again, listings times out my compilation. So not Floyd Marshall, we're going to Bellman Ford. So thank you very much, Nick, for providing me a juicy implementation. Please forgive me presenting this in Notepad because I haven't just installed Windows last week. I dislike Windows very, very much. So you'll have to forgive me for that. But so all we're doing here is we are setting the values, upper bounds of our values for all of our vertices to infinity, and then we're setting out that particular pre. If I remember what, can I remember what pre? Oh yeah, our source weight will be 0. Our pre-weight will be none. So that's fine. We're just setting up the graph, and then this is what a relaxation does. So it looks awfully similar to what happens in Dijkstra's, in that if our vertex going through a intermediate vertex is greater than the path going through what the existing weight at that vertex is plus another vertex, well, we simply have to update the distance as following. And then simply to perform this, all we do is we relax every edge over across all vertices. So all we do is we go for I in range of things because, well, the massive, as Nick has commented here, the massive path. So we're going through starting at every single vertex. So we relax n times, and then for every vertex we relax each edge. So each time we're just looking at the surrounding nodes and reducing them progressively. And then at the end here is just a simple check. It doesn't really add any complexity because we're already at v cubed overall complexity here. It just adds v squared on at the end to check if we get that negative edge weight cycle, which is very nice. Overall, this will give us a complexity if we go back down to the whiteboard. Overall, this gives us a complexity of order vertices and edges because we need to go over every edge for each vertex. We need to relax every edge for each vertex, which in the case of a fully connected graph, which we now know what that is, will be v cubed because you'll have as many vertices as edges, or like v cubed minus 1 if you want to take the approach of a tree or something like that. The last thing that we're going to cover today, perhaps rather brief, if not rather briefly, is we're going to look at the Floyd-Warshall algorithm. And this is the canonical solution to the all pairs shortest path problem. And what I mean by that is we'll get out our final piece, hopefully what is our final piece of paper for today. I know, lucky me, I realized I had more paper than I thought I had. Solves our all pairs. So I'm just going to draw some random graph. Like this. And this probably looks very weird because it's just random. And all this is going to show us is if I go 1, 2, 3, 4, 5, 6, 9, 10, it's just going to give us the shortest path between any vertex and any other vertex. Now, one solution you might think, perhaps slightly more naive solution, would be just say, we already have a perfectly good single source shortest path algorithm, Dijkstra's, or we can just use Bellman-Ford. So if we use Dijkstra's, what we'd have to do is we'd have to apply Dijkstra's for every source. So essentially what you get is you get O order v plus e v times, because you have to apply it once to every single vertex, guaranteed. And so that, if you expand out the complexity, that gives you ev squared plus v squared, which in the worst case gives you an order of v cubed plus v squared, which isn't particularly nice to look at. The second case we're going to look at is the nice thing about Floyd-Warshall is Floyd-Warshall, the implementation is stupidly simple in that it's just 3 for loops and it's order v cubed, which in the worst case is significantly better than our Dijkstra's over all sources. Now in some cases you might be able to escape when you have like a very sparsely connected graph, you might be able to escape with getting a slightly more efficient Dijkstra's, but those cases are very few and far between, and if you're asked to do all pairs, most of the time you'll be looking at doing Floyd-Warshall. So what we're going to do, before my voice dies, is we're going to get out a sample implementation of this. And it's probably going to look a bit crap, but there's no syntax highlighting. And I'm just going to ignore the print solution for now. Just going to ignore the print solution for now because it's not really important. The important bit is that it's really simple implementation. It's 3 for loops, which in terms of groundbreaking algorithms that do really impressive things, it kind of almost seems too good to be true. But let's go dig in. Let's dig in. So once again, I've done this in Python because we enjoy Python. Python's a nice language, and we have this distance here, and this is simply a very convoluted and interesting way of representing an adjacency matrix in Python data structures such that it's reasonably efficient to look up and list things. Like you could probably realistically you could get away with just having two arrays. So you could have a weight array, or you could just have the graph, which would just be that, and then you could have the distance array or path array, which would also be just that as well. And depending on whether your graph is undirected or directed, you might get symmetric paths. It might be better off using a different representation, but for the purpose here, what the magic happens in this line here, and for those of you who've done DPs before, this screams I'm a DP, because I am looking at a table of things that I already have and taking some appropriate value from it. And I'm going to take a trip over to the whiteboard here to cover off the end of this session. And what Floyd-Warshall does is it abuses that optimal substructure about as much as you can. What it's really doing is it's just saying, I have some vertex here, and I have some paths of nodes to get to a vertex here, and I'm trying to get to another vertex B through some adjacent node here. And so what it's doing is for every start node, it's checking if the shortest path lines up at this point. Now it's one page. So it's basically saying if this, what it's doing is it's checking all these shortest paths and it's checking all of these shortest paths. So it's checking all the shortest paths from A to B, all the shortest paths from A to C to combine them into one optimal shortest path. And if we look at that critical line and what it's asking us to do, it's basically saying the distance from our node I, so if we name this I, J, or I and J, our distance from I to J overall is going to be the minimum of the distance that already exists through some path and the distance from taking some intermediate node. That's all it's saying. And it's applying this logic for every possible intermediate node for every possible set of paths, which intuitively kind of works. It's simply saying, is there a possible shorter path that I can take between these two nodes and everything else? And it slowly builds upon that optimal substructure in that if a shorter path exists, well, we can just ignore this intermediate node because it won't ever be a part of our shortest path. Which is pretty interesting. And if for those of you interested, the base case is just the distance from a node to itself is 0. And in the first case, the distance from a node A to its immediate neighbors is just the weight of the graph, which gives you your base case for the DP. And then you can just keep on going there. And that's how Floyd-Warshall works. It's a very nice way. I have heard stories that for stupidly large amounts of vertices, you can gain some efficiencies in Floyd-Warshall, but you'll have to ask Lord of DP's Max about that and everything else. That's everything I had to cover about graph algorithms today. I hope some of it made some sense to you. It perhaps wasn't as slide intensive as last week. I don't know whether that's a good or a bad thing. I'm going to put my webcam back in its normal spot so it can sit there. Nice. Anything else? That. So, thank you very much everyone for attending. It was great to have 4 to 6 of you here for the past hour and a half. If you have any questions, feel free to chuck them through to me on Slack. I'm generally around there quite often, and if you want any more competitive implementations of any of the algorithms mentioned above, I'd be happy to provide those. I just haven't gotten time to chuck them in Beamer slides just yet. Not that doing it in PowerPoint would have been any more efficient. Also, if you check out the social channel, there's the dude who did something on the Turing completeness of PowerPoint. It's pretty awesome. Other than that, I'm going to chuck off the screen. So, I'm going to take that as a no for questions and shut off the stream.